kind of radiation, and it's very important in who's throwing that. Okay, not important. We continue. As you see in the picture, you see that there was many applications and many natural phenomena that require the explanation and the theory development from the thermal physics or thermal radiation. And radiation is a type of heat transfer that not require any medium. Like you will see in the picture, you see some astronomy application for the thermal radiation, and also some thermal imaging or temperature scanner that recently famous due to COVID-19 pandemic. And also like the cosmic background radiation, as you will see the blue circle there. So teacher, can we go to the next slide? Hank, you read this one.
In physics, radiation is the emission or transmission of energy in the form of wave or particles through space or through a material medium. These include electromagnetic radiation, such as radio wave, microwave, infrared visible light, ultraviolet, X-rays, and gamma radiation. Then particle radiation such as alpha radiation, beta radiation, and proton radiation, neutron radiation, which is particles of non-zero rest energy.
So here
Next
everyone
slide.
you see that the slide here you got see the cloud chamber here. As everyone has learned before in SPM, we use cloud chamber to observe each kind of radiation. And just like what Hank explained before, radiation they got two types. One is the particle-based radiation, like the beta and alpha ray, and another one is the electromagnetic wave. And you see the boy here, a scientist here who is observing the radiation with the light above the cloud chamber. So, but what we focus here is on electromagnetic radiation, which is the kind of thermal radiation. And thermal radiation did not involve any particular radiation like alpha or beta. We just discussed about the electromagnetic spectrum. That means which only involve the electromagnetic wave, the kind of radiation we discussed here. So next slide. And everyone you see here, here is the photo taken from the cloud chamber when the radiation pass through. You will see some electrons or low energy electrons or some alpha ray or some proton, some helium particle, some helium ion particles in the cloud chamber you will observe here. And you will see that the pathway for the electron is not quite clear, but the pathway for the alpha and proton is quite clear because due to the mass and high ionizing power of the alpha particle. While for the thermal radiation, we can't really observe much from the cloud chamber. We can only observe it from the spectrum of electron. Okay, next slide. T, you want to say?
Can. So for next is heat transfer by radiation. Thermal radiation. Thermal radiation is the energy emitted by matter as electromagnetic wave due to the pool of thermal energy that all matter that has a temperature above absolute zero. Thermal radiation can propagate through vacuum and is an emission of electromagnetic radiation that carry energy away from the surface. So why object emit radiation in temperature above is to allow the object achieve thermal equilibrium of the system.
Next slide.
Sure, next slide. Yeah. So here, what is thermodynamic equilibrium? That what we talked about before is thermal equilibrium, and thermal equilibrium is one kind of situation that involves in thermal equilibrium. For attaining the state of thermal equilibrium, the following three types of state must be achieved. The first one is thermal equilibrium, which deal with the temperature. The temperature of the system does not change with time and have the safe value of all point of the system, which means that if they got two systems that with different temperature, there will be an exchange of heat until the temperature of both systems are same. And the second one is mechanical equilibrium that we already discussed before in third chapter and even fourth chapter, that there is no net torque and no net force on act on the system. So the system can be only either stationary or with constant velocity and or rotating itself with constant angular velocity. No net torque, which means no force on the any point from the other point that will create a net torque. And the last one is chemical equilibrium. That means no chemical reaction will take place, or there will be a chemical reaction that but does not change the chemical compositions of the system. Next slide. So here are the founding fathers of thermodynamics here. But the most important one is Ludwig Boltzmann, James Maxwell, and also Johannes van der Waals. And the most we hit is James Maxwell and Louis Boltzmann. For both of them, the developmental theory for both thermodynamic and heat radiation transfer. Next. Hang or T, you either.
Next is radiation follows laws of reflection. Energy such as heat transmitted by radiation is called radiant energy. Thermal radiation consists of combination of wavelengths. When thermal energy is directed to a surface, some of the radiation is absorbed and some is reflected. However, for certain materials, the radiation may be transmitted right through the material. Some of the examples of radiation are the transfer of heat from sun to the earth, intense heat from glowing coals in a fireplace, and heat emitted from automobile radiator. Next.
You want or me?
I think you can explain first.
Okay. Okay. The next is radiation obeys the law of inverse square law. I know everyone maybe know already what is inverse square law from the chapter of universe gravitation. Like same with Newton's law of universe gravitation, which means that the magnitude of the radiation same with the magnitude of gravity is also decreases with the distance square from the source of the gravity or from the source of radiation. Which means the further away the radiation from the source, the magnitude will be decreases due to the increase in area of square of area from the distance of the source. As you can see in the picture, as light is also a kind of electromagnetic radiation that in our visible region. So I use the light as the example. You can see it will be the magnitude for the intensity or the luminosity of the light is much higher when it's near the source. You can see the number 22 range from 22 to 16 to 11, 8, 5.6, and even 4 when it's 4 decibel or I from the source when it is more further away from the source of the light. So by this means the radiation will be more weaker and weaker until it is totally absorbed by a certain substance when it is more further away from the source of radiation. As you can see the area here, R, 2R, 3R from the picture on the right, the source of power will be divided by the A squared, but it's not in our SPM syllabus. Here is just for the better illustration for you all. Okay, next slide. E.
So next is Prevost theory of exchange. According to Prevost theory of exchange, a body emits radiation at a rate which is determined only by the nature of its surface and its temperature, and absorbs radiation at a rate determined by the nature of its surface and the temperature of its surrounding. So in short, a body emits and absorbs radiation just depends on its nature of its surface and the temperature of its surrounding. Next, consider a body in thermal equilibrium with its surrounding, that is, its temperature is equal to the temperatures of its surrounding. If the surface of a body is such that the body is a good absorber of radiation, it must be an equally good emitter. Otherwise, its temperature would rise above that of its surrounding. Conversely, if a body is such that the body is a good emitter of radiation, it must be an equally good absorber. Otherwise, its temperature would fall below that of its surrounding. So, for example, a black surface is the best emitter and best absorber, but a highly polished silver surface is both a poor emitter and poor absorber of a heat. Next.
So here, everyone can see that the picture of the light hit on the black surface, a white surface, a blue surface, a green surface, and a red surface. Why scientists or the physicists use the name of black body to mention that a black body as the perfect body that absorbs totally all radiation of the wavelength which fall on it and do not reflect nor transmit any radiation. This is because like it's used the intuition for our sight. If the O color is absorbed by the absorbed by a surface, we can't receive any radiation. We can't receive any visible light that enter our retina of eye, and we will see that the surface will become a black color. Conversely, if we see the white surface, which means that the three primary source of light, which is blue color, green color, and red color, that reflect totally back to our eyes. Same goes with blue color, it absorbs both red and red color light, but reflect both blue color light to our eyes. For green surface, it absorbs both blue and red light, but reflect green light to our eyes. Finally, for red color, they absorb blue and green light, but reflect red color to our light. So that's why we use the term black body to mention that the body absorbs any radiation of electromagnetic spectrum. And you can see for the metal, the picture for the metal of steel bar that it is glowing red when it is blown until a very hot temperature. It emits the light in certain frequency and wavelength to release the energy so that it will become thermal equilibrium with the temperature surrounding it. Next slide. Lee.
When black body is heated, it emits radiation of all possible wavelengths. The radiation emitted by the black body is called black body radiation. The wavelength of the radiation emitted depends on only the temperature and is independent of the material of the body. The higher the temperature of the body, the shorter the wavelength of the thermal radiation emitted. Next slide.
Hello? See?
Oh, okay. So for attention, there is no perfect black body in this world, but only body that almost approach to perfect black body. So for example, so some example of nearly perfect black body and black is next.
So here, as you can see, the sun is the perfect emitter, and as it acts like a nearly perfect black body. While the black hole is like a perfect absorber, as it's also the nearly perfect black body. I can hear the sound of the call. Something wrong with the audio. Okay, for here, I would like to talk about the intensity distribution in the spectrum of black body. Here, can you put to the next slide before I start this slide? As you can see the red bar here, the metal bar here, which is burning to a very hot temperature, you can see the red color and the blue color below, right? So for the red part of red color, the red light emitted at the upper part of the metal bar, which means that it is lower in temperature. While the blue color there will be the higher temperature of the metal bar. So teacher, can you back to the previous slide? As what I said before, like I give an example, like when the metal upper part of the metal part, if I burn in roughly to 4,000 K or 3,000 K, you can see that the visible range, the intensity of red light in 4,000 K or even 5,000 K and 3,000 K is higher than the intensity of visible blue light or violet light. So that's why when in lower temperature, the range of wavelength of light emitted is mostly in in red color or orange color. And if the temperature is much higher, like in 6,000 K, you will see that the intensity of blue light become much and much higher. And later they will become predominant the color of the light emitted by the metal bar, like the picture you see in the next slide. The bottom part is blue color, but the upper part is red color because the temperature of below of the bottom part of the metal bar is much higher. So the blue light is emitted instead of the red light. The blue light intensity for blue light is much higher than the red light. So next slide. Hank.
Next is the Stefan Boltzmann law. This law states that the total energy radiated per unit surface area of a black body per unit time is directly proportional to the fourth power of the black body's absolute temperature. The formula of energy radiated is given, where O is the Stefan's constant. The power or the rate of energy radiated is P equal to O A T power 4, where A is the surface area of the black body. For gray body, the emissivity is smaller than 1. Therefore, P equal to EOA T power 4. When a body is not in the thermodynamic equilibrium, the net power radiated is the difference between the power emitted and the power absorbed. P equal to EOA times T power of 4 minus initial temperature power 4, where T is the absolute temperature of the body and T0 is the absolute temperature of the surroundings. Next slide. The total energy radiated per unit surface area of a black body per unit time is directly proportional to the fourth power of the black body's absolute temperature, E equal to OT4, where E is the total energy radiated per unit meter square per second, O is the Stefan Boltzmann constant and T is the temperature. Next slide.
So here is just repeat with what Hank said before, but here normally for P they use dQ/dt for power because for any temperature, for any radiation absorbed and emitted at a certain range, if we just directly substitute the temperature of that moment, we can't know either the radiation absorbed or released by the certain object. So we are under the assumption that the power of or the heat rate of heat transfer is equal to rate of heat absorbed by the certain material will be equal to the net of heat transfer will be equal to 0 in thermodynamic equilibrium. But when the body is not in thermodynamic equilibrium, we need to find the net heat transfer. That means we should, in that moment, maybe the P of emitted, the radiation of emitted by the body is much higher than the radiation absorbed by the body. Don't be confused that because the radiation is absorbed and emitted at the same time, just the rate of radiation emitted and the rate of radiation absorbed is different. So we need to calculate the net radiation absorbed or emitted by using the formula P net equal to P emit minus the P absorbed, which we can come back to the Stefan-Boltzmann law, which we separate the temperature of T4 into the 3 T object minus the T surrounding, or T surrounding minus the T object. Just depend on you how you substitute the formula. And the temperature we use is in Kelvin still. Okay, next slide. Never mind. T is right.
So for example 1, an electrical heating element of 1 kilowatt has a surface area of 0.006 meters square. Estimate its working temperature. So by applying the Stefan-Boltzmann law, P is equal to area times sigma. The sigma is equal to the Stefan constant and the temperature power 4. So the calculation, the solution is shown in the screen.
So this is just a simple question, the harder one at the back. Next slide. Not this one yet, but you can see this question, example 2, is similar with the first example. You just directly substitute. For this time, is we're given the temperature, the 2000 keV heat energy. It already gives the energy and the wavelength. It just asks us to calculate the temperature. We just substitute back the value into the formula and we do some algebra and get back the value. So example 1 and example 2 is still the simple question. The next question will be what we want to discuss for. Teacher, next slide.
This one will be the formula E equals to HF, right? Is it? What's the formula for this? This is wavelength, and this one is the heat energy. Lambda times. This is lambda times.
The Wend's law. The Wend's law.
So Wend's law is the lambda times
temperature equal to that constant.
This is lambda times with the Q.
Tm.
Q.
Tm. Q or Tm.
Q, right?
Teacher, temperature.
Temperature. Oh, it's the temperature. So it's
yeah. Lambda times temperature equal to constant.
Lambda times temperature. Okay. We are lambda times temperature equals to constant.
Yeah, the constant is 1.8 um.
Okay.
That's means we just do some algebra, put there, divide, get the answer. Here are the 2 easy questions.
Okay.
So next question. And here is what we want to find for. Right, here consider the total area of human skin is here like that with temperature of 35 degrees. They calculate the need of energy radiated for skin in the room temperature is 21. As we can use the theory of previous exchange. As here, the surrounding temperature is lower than the body. That means the rate of energy emitted by the body is much higher than the energy emitted by the absorbed by the body. The temperature of the will be lower. That means the rate of emit is higher. And the second question, you see the cylindrical electric element of length 25 and diameter. It gives you the length and give you the diameter, which means they need you to find the area. So calculate temperature in use if it behaves as a black body. And the user case in the example given, if there is no given E, we will directly assume the body is the perfect black body. If the question they will give the E, the emission constant, that means the body, we can't directly assume it as a black body. Teacher, next slide. So here the first question, you must put a constant E in front of the Stephen Boltzmann law, because it is not a perfect black body. For the second question, as you already assume it as a perfect black body without giving us the number of E, but we need to find the area. So that's why we need to substitute the formula of area for the wire before we can get the answer. Okay, teacher. So here the application for thermal radiation, like in COVID pandemic, in any airport, any public space, any government department, we need to do some thermal scanning for our temperature by using the thermal radiation emitted by human body scanned by any instrument to detect our body temperature. And the next and the most important one is the use of thermal radiation in astronomy observation. Like you can see the picture there, NOAD. It is a Nebula 17. You can see both pictures. There's actually the same picture, but the left one is only visible light, but the right one is the visible light with the infrared ray scanning. So is it important to let us know and detect the motion of any astronomical object? And the most important one is, you can see the below one. It was the evidence for Big Bang theory, the expansion and the origin of the universe. In COBOL, there were three astronomical telescopes to detect, used by humans to detect the evidence for Big Bang theory. As you can see, the green one is it means for the higher temperature. As you can see, the globe is much more smaller in year after year. It is a theory to expand that the universe is expanding, so that the universe is much more cooler than before. So by going on, we can know that the history of our universe and find more evidence of the origin of the universe. Teacher, can you turn to the next slide? And here you can see the Hubble telescope to detect the thermal ranging for the universe. And maybe some may not understand what I say and what you see in the picture before. You can see the picture here. The universe expands. That means the globe will be much more further and further the star you can see. Teacher, can you turn to the previous slide? So can you see back the circle, the black circle? The circle there, you can see that the globe is much more further and further the point between. So it will become the evidence for us to know that the universe is expanding. So teacher, next slide again. So so here you can see that the star is expanding and the globe much more will be similar with what the picture you see before. And in my slide, my presentation. So here's some funny meme.
Okay, where's the thing?
Hmm?
Ah, there. Ken, last word.
Okay, my last word. T, you say lah. You help me a lot leh, T and Hank.
No lah, Yuan.
You have 3 minutes, faster. Limiting win time, 3 minutes.
Hank, T, say something ah. You contribute so much ah. So anyone of you want to take pure physics in university later? Is that Malcolm? I think I have nothing to say.
Okay, so thank you, Ken, and who's the thing? Ken and who's the member? Forgot already.
Li Hangyuan and Yi Hao.
Yi Hao, and those who are member in this presenting power slide. Okay, it's so much so much detail you have done. Okay, and thank you. We only have like 2 minutes, so tomorrow, who's it? Maverick, right? Maverick, is it you tomorrow?
Yes, sir.
Okay, so you prepare for tomorrow presentation. Okay. Have you done or not?
I sent you, sir.
I sent
Done for a
already.
very long time.
Okay. So good job, good job for all the members of this radiation PowerPoint slide. Okay, see you tomorrow. I'm hoping Maverick, can you do better than them?
The video win already.
Okay. Okay. See you tomorrow. Okay, sayonara. Bye bye.
With your sayonara.
Sayonara.